three small things to share with you here, 5 minutes for each, plenty of time. I'm going to do the same thing. So this is an alternative now. I'm going to show you two method boxes that does the same thing once again, but in a slightly different way in the outset, not using distributions actually. So, why actually would we even think of that? Why don't we just use distributions? But why would we not just use distributions? What is the problem in using the exponential distribution or the normal distribution? Potential problem. Well, I usually don't ask you questions, so probably you don't. He's just answering his own questions anyway. So, yeah, but now I thought I had a minute, so let's hear. Yeah, it could turn out to be the wrong distribution. I couldn't have said it nicer myself. Maybe this assumption is wrong. And you could always be challenged by that. If you submit a paper to Nature, or if you go to the research director of Novo Nordisk with your results and tell him we're going to spend 5 billion in that direction because I did my analysis based on the exponential distribution. I got this result. My conclusion is, go spend the money. And he tells you, he asks, are you sure that's the exponential? I don't know. Back to your desk and try to find out if you can be sure about that, right? You need to justify it somehow. It needs to be either justified by historic results, that this kind of, maybe by some kind of formal probability arguments like blah, 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 blah. This kind of system usually behaves like an exponential. Yeah, hey, usually it's fine, but I want to be sure that this system behaves like the exponential. I need to go investigate it. I need to justify it. Or I'm trying to convey the results without that assumption, because if I don't have that assumption, he cannot attack me on the assumption. I'm giving you a result that is true, and I don't have any assumption about distribution. Usually there are some assumptions going along with us, but not a distribution one. Here's a little example a little silly example, maybe again, but trying to illustrate with some data that are supposed to be somehow obviously non-normal in their structure. That's how these silly data was chosen originally. It's a very old experiment. I don't even have the formal citation for it here. Very old one back then when our mothers were smoking during pregnancy, before and after. There is an explanation to everything. So here we go. This lady, this woman, smoked 8 cigarettes before she gave birth, and then after she gave birth, she only smoked 5. Way to go, young lady. This one have an even better change from 24 to 11. Nice. This one really good, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 paired observations before, after cigarette use, right? Classical paired t-test data. So you were taught that a few weeks ago, right? So if you were to use those tools that I gave you, hoping for the CLT, but here's the data. Let me see, here's x1, x2. I compute the difference because that's what I taught you. If we have a paired setting, we should, to do the paired t-test, we could just compute the 11 differences. And such data, integer data, cannot be normally distributed, right? Doesn't really make sense. Normal can have on any value. So such integer categorical type data could not essentially truly be normal data. So anyone could attack you there and say, I don't believe the normal. Maybe you would argue, yeah, maybe it's not normal, but I'm not sure it makes a big difference for that. Maybe it's almost normal, and I have the CLT. My professor told me it's a magic thing. I use the CLT. What is your N? It's 11. I Google, usually rules of thumb says at least 30 to be sure, and even still it's rule of thumb. Do I want to invest 5 billion on a rule of thumb on an introductory stats book? I'm sure my score would not. So we have to look into it. What can we do? Let me share with you how we can do statistics. This is the non-parametric bootstrapping idea, the resampling idea illustrated in a little box here. The idea is to simulate the sampling distribution. And I emphasize again, not by assuming some distribution like we did before, but by doing sensitivity analysis or resampling from the data itself, right? I have my 11 data points. I try again and again to see how could 11 data come out? So I resample my own data with replacement. In R, if I should do it explicitly, I'm just showing you how this looks when I replicate it 5 times. This is the K number, which is supposed to be 100,000 in a minute, right? I'm not showing you 100,000. I'm trying to show you 5 of them, the 5 first ones, to illustrate what's going on. I use the R function called sample. I have my 11 diff numbers. These are my data. The diff, that's my data now. I call it diff. 11 data points. I sampled them, and if I don't say like that, it just shuffles them, permutes them. That's not what I want. I don't want just to permute. That can be used sometimes in other contexts, but now I'm resampling them, which means here I have one version of the resampling. The T here is just a transpose to get it on a form so that we can look at them. Let's look at the 5th one, just to make a point. Look at the 5th one. The 22 actually came twice, and the 0 actually came 3 times. My raw data was only 1 0 and only 1 22, but that's just to emphasize the fact that I take repeatedly samples of 11 numbers taken with replacement. So I take a sample, I put it back, I take a sample, I put it back, I take a sample, I put it back. So it's part of, it's on purpose, it's part of the structure here that observations can come again and again. And some are not there, that's the idea of it. That gives us, that will show us how different can that go, how different are the means or the medians or whatever I compute from sample to sample, just by looking at the data themselves. Shows me how can it come out. I simulate the sampling distribution. By raw resampling, by non-parametric resampling, there is no distribution in this. Can you see it? And here are my 3, 1, 2, 3, without a lot of explanation or comments. I replicate 100,000 times with only 11. There's a little twist to this that we don't spend seconds on now. With only 11, there is a limit to how many different there are. But it doesn't really invalidate what we do, but some of them might come up again and again, actually. But anyway, if there are more than 11, the number of different possibilities becomes huge, and we don't have that issue. But it's still okay. But I have a comment about that in the note, if you want. The procedure is still fine. Then I do the same thing as, now you can see here is the difference to before. This is that makes the non-parametric bootstrap. I don't have a distribution here. I use the data itself. In a way, you could say I use the data distribution. I use the empirical distribution as the one that I sampled from. Not an exponential, not a normal, not a log normal. The observed empirical distribution is used for my resampling. And this is how it's done in R. This is the same, right? Compute all the means. Look at the quantiles. Here it is. Your first non-parametric bootstrapped confidence interval. No distributional assumption. It can be used to investigate how much does it actually, how important and what does it bring to make the distributional assumption? Do I get a different result by the distributional assumption or not? Often we'll see we don't get dramatically different, actually, which is nice, reassuring. Then I can go to my score and say, spend the 5 billion, I'm happy. Here is the formal method box, the first of them, of the 2 you will see. Non-parametric bootstrap confidence intervals for a single computed feature, including the mean or something else. Right? Could be the mean, could be something else. Simulate by randomly sampling among the available data with replacement. That's my wording for the thing that I've done. No distribution. Calculate, look at the quantize. Exactly the same as before. Right? One more example. We have joined in 2 of the lectures now, Gandalf, which is fine. Little example. What if I do the median instead of the mean? I can do that also. It was part of my method box. Now here's before I exemplified with the mean, now I exemplified with the median, and it's almost now boring to say, but it's 0.1, 2, 3. The only difference is that I write median instead of mean, and I get the same thing. You can see it's the same thing coming again and again here. Let me see. Yes, and now we jump to the last part, actually. This was, which is the last